In this video, we discuss scalar multiples of vectors, how to express a horizontal or vertical vector as a scalar multiple of a unit vector, and how to express any vector as a linear combination of unit vectors. We also discuss several notations for the components of a vector, and then we finish with a couple simple examples. So we begin by discussing scalar multiplication. And a scalar is just a number, and when we multiply a vector by a scalar, it simply scales that vector or stretches it. So in our first example, we're given a vector v, and we're asked to draw the vector 2v. And one way to answer this correctly is to say that you just stretch it by a factor of 2 and leave the direction the same, and there's 2v. But I could also go back to fundamentals here and say, what does it mean to multiply something by 2? And what it means to say 2v is add v to itself twice. That's v plus v. So that's just another way to look at it. And if I vector add v plus v, I put the tail of the second on the head of the first. I draw a vector from the tail of the first to the head of the second, and I get the exact same answer of a vector twice as long and pointing in the original direction. Next, we take a look at some unit vectors. So a unit vector in general is just any vector that has a length of 1, but we're particularly interested in the unit vectors that point along the coordinate axes. So first is our horizontal unit vector. Again, that has a length of 1. And it points in the positive x direction, and that gets a special name as an I hat. The next one's a vertical unit vector. That has a length of 1 and points in the positive y direction, and we call that j hat. And if we're in a three-dimensional space, we would just have another unit vector pointing in the z direction, and that's called k hat. In the next example, we start to get a sense for why these unit vectors might be useful. We're asked to express the following vectors as multiples of I hat or j hat. And the first one is a vector of length 5 pointing exactly in the positive x direction. Well, that's just a scalar multiple of the unit vector that's pointing in the positive x direction. It's just 5 times I hat. The next one points in the positive y direction and it has a length of 3. Well, that's just j hat stretched by a factor of 3. So that's 3j hat. And we can do this for any vector. It doesn't have to be pointing perfectly horizontal or vertical. In the next example, we have a tilted vector, and I've labeled the magnitudes of the components here. So the x component is a vector of length 10 pointing in the positive x direction, and the y component is a vector of length 6 pointing in the plus y direction. Each of those vectors can be represented as a scalar multiple of a unit vector, and so I could write v as 10 I hat plus 6 j hat. So this is true for any two-dimensional vector. I could write it as a linear combination of the unit vectors I hat and j hat. And that phrase linear combination just means a sum of constant multiples of those things. Next, we're going to quickly summarize some different notations for two-dimensional vectors. And all of these notations extend naturally to the three-dimensional case. You would just tack on a z component, and the unit vector pointing in the z direction is called k hat. So here's a few different ways of writing the vector v. We could start with the unit vector notation. You write it as a linear combination of I hat and j hat. Alternatively, I can just make a list of numbers telling me the x and y coordinates of that vector. And if it was a 3D vector, I would tell you the x, y, and z coordinates. So in this second notation, I've done that as a row vector. So it's a list of numbers horizontally separated by commas, wrapped in parentheses. Now there are other notations for this. It's perfectly fine if you want to use brackets and skip the commas. And a lot of math textbooks use pointy brackets as well. Now the argument for using pointy brackets is to distinguish a vector from an ordered pair. But in physics, we typically just use this parentheses notation, and we don't get confused with ordered pairs because we understand by context that we're talking about an arrow, a vector, and not just a point in space. Finally, we have the column vector notation. So you can just list the coordinates of your vector vertically and wrap it in brackets or parentheses, or in some math textbooks, giant pointy brackets. In our example, we're asked to write this vector v in terms of unit vectors, and then as a row vector, and then as a column vector. So this v is going to be 2 I hat plus 3 j hat. Or as a row vector, it's just a list of numbers, 2, 3. Or as a column vector, I prefer to use brackets for those. It's just the number 2 and then the number 3 on the bottom, and wrap it in brackets. So let's wrap things up with a couple extra examples. In the first one, I'm asked to express this vector as a linear combination of unit vectors. And this time I'm not given the components. I have to compute those myself. So we have to do a little bit more work. And that x component is given by the hypotenuse times the cosine of the angle. Into 3 sig figs, that gives me 96.4. And the y component will be hypotenuse times the sine of the angle. Into 3 sig figs, that gives me 115. And I was asked to write this vector as a linear combination of unit vectors. So I have 96.4 I hat. Again, that's a scalar multiple of the unit vector pointing in the positive x direction. That gives me a length of 96.4 pointing to the right. And then I vector add to that 115 in the j hat direction. Finally, we're asked to compute the magnitude and direction of a vector that's given as a column vector 1, 3. And it would be nice to have a picture of this thing. So my vector has components of length 1 and 3, 1 pointing to the right, 3 pointing up. And I'm interested in the magnitude of this guy and the angle with respect to the x-axis. And so the magnitude is just given by the Pythagorean theorem. I take the square root of the sum of the squares of the two legs of that right triangle, and I get square root of 10 out of this. And the square root of 10 is about 3.16. Then we want the angle, and that's given by an inverse tangent, the angle whose tangent is 3 over 1. Into 3 sig figs, that's 71.6 degrees. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.